Hello everyone, in this lecture we will learn how to calculate eigenvalues of a matrix. This is an important topic from net examination point of view. Okay, so let's start. So we have a matrix A and it is acting on a column vector x. Then on the right hand side we have some value lambda and the same column vector x. Then this is known as eigenvalue equation. There are some special column vectors for this matrix A for which we get the same column vectors multiply with some value lambda on the right hand side, and these vectors x is known as eigenvector of matrix A with eigenvalue lambda. So this equation we can imagine as A is the n cross n matrix and it is acting on a column vector n cross 1 column vector. Then on the right hand side we have same column vector multiply with some value lambda. So if we have an identity matrix, so identity matrix have diagonal entries as 1 and all the non-diagonal entries are 0. When it will act on some column vector, some let's say x1 x2 xn, then on the right hand side we will get same column vector when we do the matrix multiplication. So any column vector x we can write it as I acting on x. So this we use in the above equation. Then we can write ax equals to lambda ix. Then we take this lambda ix on the left hand side. Then we can write ax minus lambda ix equals to 0. So a minus lambda a matrix acting on column vector x is giving me 0 column vector on the right hand side. So one trivial solution of this equation is just x is the 0 column vector. So this is the trivial solution. But a non-trivial solution for x exists if this matrix A minus lambda I is a singular matrix. So the determinant of this A minus lambda I is equals to 0. This is known as characteristic equation, and we have to solve this equation to get the eigenvalues of matrix A. If matrix A is a n cross n matrix, then it will have n eigenvalues lambda 1 lambda 2 lambda n, and the set of these eigenvalues is known as the spectrum of A. And if we want to find out the eigenvalues of some matrix A to the power m, then they will be just lambda 1 to the power m, lambda 2 to the power m, lambda n to the power m. This is the spectrum of A to the power m. This we can easily see from the eigenvalue equation, which is ax equals to lambda x. Then a square x will be a into x, and ax is the lambda x. Here lambda is just a number, so we can take it outside, lambda ax. Then again ax is the lambda x, so this is lambda square x. Then we can generalize it to show that a to the power m acting on x will give me just lambda to the power m x. Now we will see some important points related to eigenvalues. So the first important point is that the sum of the eigenvalues is equal to the trace of the matrix A. So trace is the sum of the diagonal entries, and this trace is equals to the sum of the eigenvalues, and the product of eigenvalues is equals to the determinant of matrix A. These two properties are very important for eigenvalues. Third point is that for a real matrix, each eigenvalue is either real or if it is complex, then its complex conjugate is also an eigenvalue. So either all the eigenvalues will be real, but if a minus a plus ib is the eigenvalue of a real matrix, then a minus ib will also be an eigenvalue of the same real matrix. Fourth point is that the eigenvalues of a Hermitian matrix are real. So Hermitian matrix is a matrix for which h dagger equals to h, and the eigenvalues of Hermitian matrix are real. Fifth point is that eigenvalues of an anti-Hermitian matrix are purely imaginary. So the eigenvalues of anti-Hermitian matrix are in the form of iota times some number. Now the eigenvalues of unitary matrix are unimodulus. So if lambda is the eigenvalue of a unitary matrix, then mod lambda square is equals to 1. So lambda is in the form of exponential I theta for a unitary matrix. Now the last important point is that if A is a matrix with all the entries as 1, then this is a special matrix, and the eigenvalues of this matrix we can calculate from by solving the characteristic equation. But there is only one non-zero eigenvalues, which is equals to n. This is n cross n matrix, and all other eigenvalues will be equals to 0. So n minus 1 eigenvalues as 0 and 1 eigenvalue as n. Okay, so now we will see some important examples that are also previous year's questions from CSIR NET exam. So question 1 is a 2 cross 2 matrix. A has eigenvalue e to the power I pi by 5 and e to the power I pi by 6. So the smallest value of n such that a to the power n equals to identity matrix. So the options are 20, 30, 60 and 120. This is from December 2012 NET exam. So the A has eigenvalues as exponential I pi by 5 and exponential I pi over 6. Then a to the power n will have eigenvalues as exponential I n pi over 5 and exponential I n pi over 6. But a to the power n is the identity matrix, and identity matrix has eigenvalues as both the eigenvalues are 1 for identity matrix if it is a 2 cross 2 identity matrix. Then exponential I n pi over 5 equals to 1 and exponential I n pi over 6 is also equals to 1 to satisfy this equation. Now 1 we can write it as exponential I to m pi. Then we compare and we will get n over 5 equals to 2m. So n is 10m, where m is an integer. So n can take values as 10, 20, 30, 40, 50, 60, etc. And here exponential I n pi over 6 is equals to n exponential I 2m pi. So here n over 6 equals to twice of m. N is in the form of 12m, where m is an integer. So n can take values as 12, 24, 36, 48, 60, 72, etc. So the smallest value for n for which these two conditions satisfy is 60. So n equals to 60 is the correct answer. Now the question 2 is consider the matrix M equals to 0, 2i, 3i, minus 2i, 0, 6i, minus 3i, minus 6i, 0. So we have to tell about the eigenvalues of M. So the A option is minus 5, minus 2, 7. B option is minus 7, 0, 7. C option is minus 4i, 2i, 2i, and the D option is 2, 3, 6. So this is from June 2014 net exam. Now this matrix looks special as when we calculate the dagger of this matrix. So to calculate dagger, first we complex conjugate all the elements. So 0 is just 0, 2i will become minus 2i, 3i will become minus 3i, minus 2i will become 2i, and so on. 0, minus 6i, 3i, 6i, 0. And we transpose this. So 0, minus 2i, minus 3i, 2i, 3i, 0, minus 6i, 6i, and 0. But this is equals to M. So M dagger equals to M, so M is a Hermitian matrix. Now we know that the eigenvalues of Hermitian matrix are real, so option C is not possible. Now the trace of this matrix M is 0 plus 0 plus 0, sum of the diagonal entries. Trace of M is 0. So it is also equal to the sum of the eigenvalues. So option D is not possible because the sum of eigenvalues in option D is 11. So either option A is correct or B is correct. In one of the option, like in option B, 0 is the eigenvalue. This is only possible if the determinant of this matrix M is 0. So we will calculate the determinant of this matrix M. If it is 0, then option B will be correct. If it is non-zero, then option A will be correct. So we will calculate determinant of matrix M. 0, 2i, 3i, minus 2i, minus 3i, 0, 6i, minus 6i, 0. So we will expand from the first row, minus 2i, 0, plus 18i square, plus 3i, 12i square, minus 0. So minus 36i cube plus 36i cube, which is equals to 0. So the determinant of matrix M is 0. So 0 must be an eigenvalue of matrix M. So option B is the correct option. Minus 7, 0, 7. These are the eigenvalue of M. So without solving the characteristic equation, we can tell about the eigenvalues of matrix by remembering those important points. Now the question 3. Which of the following cannot be the eigenvalues of a real 3 cross 3 matrix? Option A is 2i 0 minus 2i. Option B is all eigenvalues as 1. Option C is exponential I theta, exponential minus I theta 1. And option D is I 1 comma 0. So this is from June 2017. Now it is given as the matrix is a real 3 cross 3 matrix. So for a real matrix, all the eigenvalues are real, or if one of the eigenvalues is a complex, then its complex conjugate will also be an eigenvalue. So in option A, 2i is the eigenvalue, but minus 2i is also present in the spectrum of real matrix. So this is the possible eigenvalues of a real matrix. B option, in B option all the eigenvalues are 1, which are real. So B option is also possible eigenvalues for a real matrix. In option C, exponential I theta is present, then exponential minus I theta is also present. So these eigenvalues can be the eigenvalues of a real matrix. But in option D, I is present, but its complex conjugate minus I is not present. So option D is the correct option, as I 1 comma 0 cannot be the eigenvalues of a real 3 cross 3 matrix. Okay, so now the question 4 is the eigenvalues of the 3 cross 3 matrix, where this matrix M is given as A square AB AC AB B square BC AC BC and C square are. Option A is A square plus B square plus C square, comma 0, comma 0. Option B is B square plus C square, comma A square, comma 0. Option C is A square plus B square, comma C square, comma 0. And option D is A square plus C square, comma B square, comma 0. So this is from June 2020. So to get the eigenvalues of this matrix M, we have to solve the characteristic equation. M minus lambda I determinant equals to 0. So here A square minus lambda, B square minus lambda, C square minus lambda, AB, AC, AB, AC, BC equals to 0. So we will expand from the first row. A square minus lambda, B square minus lambda, C square minus lambda, minus B square C square, minus AB, AB C square minus lambda, minus AB C square, plus AC, AB square C minus AC B square minus lambda equals to 0. Now we will multiply B square C square plus lambda square minus B square plus C square lambda minus B square C square minus AB ABC square minus AB lambda minus ABC square plus AC AB square C minus AB square C plus AC lambda equals to 0. So these terms will cancel out. Then we will get A square minus lambda, lambda square minus B square plus C square lambda plus a square b square lambda plus a square c square lambda equals to 0. Then we will multiply a square lambda square minus a square b square lambda minus a square c square lambda minus lambda cube plus b square c plus c square lambda square a square b square lambda a square c square lambda equals to 0. Then these terms will also cancel out, and we will take lambda square as common. A square plus b square plus c square minus lambda cube equals to 0. Then again we will take lambda square as common. A square plus b square plus c square minus lambda equals to 0. So lambda equals to 0, 0, a square plus b square plus c square. So these are the eigenvalues of matrix M. So option A is the correct option. Now the question 5 is the same type of question as question 4. The elements of a 3x3 matrix A are the products of its row and column indices. So Aij elements of matrix A are in the form of Ij, where I and j runs from 1 to 3. So the eigenvalues of capital A are: A option is 7, 7, 0, B option is 7, 4, 3, C option is 14, 0, 0, and D option is 14 over 3, 14 over 3, 14 over 3. This is from June 2019. So if we write the Aij is given as Ij. So if we write matrix A, then the first element will be 1 into 1, just 1. Second element 1 into 2, which is 2. Then 1 into 3 is 3. 2 into 1 is 2. 2 into 2 is 4. 2 into 3 is 6. 3 into 1 is 3. 3 into 2 is 6. And the last element is 3 cross 3, which is 9. So this is the matrix A. And if we see the previous question, where the matrix M is A square, AB, AC, AB, B square, BC, AC, BC, and C square. And when we put A, B, C as 1, 2, 3, we will get this A matrix. So we can similarly solve that characteristic equation to get the eigenvalues of this matrix A. Then we will get the eigenvalues in the form of A square plus B square plus C square, 0, 0. Same answer as the last question. But here A and B and C are 1 to 3. So 1 square plus 2 square plus 3 square, 0, 0. So 14, 0, 0 are the eigenvalues of this matrix A. So option C is the correct option. Okay, thank you.